A bit too early. Oh God. Okay, I think we can start,
Yeah.
right? There's like 4 minutes in. So yeah, we can also like close in. Okay, so today we're very delighted to be hosting Dr. Giada Pastorelli from University of Padua. So a little bit of biography of Giada. So Giada obtained her PhD in 2019 at the University of Padua, and it was followed by a postdoc position. Then she moved to Baltimore and joined the Interstellar Medium ST group to start her second official postdoc. And since then, she's been doing a couple of postdocs here in Padua, and we're very delighted to have her back. So her research mainly focuses on stellar population synthesis, simulations, and star formation history, and also model calibrations. And her talk today is also about the resolved stellar populations in the era of larger scale surveys. And we're very much looking forward to hearing this talk. Thank you so much for accepting our invitation. And yes, the floor is yours. Please take it away.
Thank you, Fatima, for the introduction, and both Julia and Fatima for inviting me to give this talk. So today, the idea is to tell you a little bit about the work I've been doing about modeling resolved stellar population, mainly for photometric surveys, but um, there are some aspects that I think might be relevant also for instrument like WST, and of course there are topics and aspects that may benefit from WST observations. Um, okay. So my research, let's say, revolves around three main aspects. So basically, I use stellar evolution models and to produce stellar population models to interpret photometric data of a resolved stellar system, and I also use stellar population models to compare with data in order to constrain stellar evolution models themselves. And another thing that can be done with stellar population models is to support future missions design and observing strategy. Um, so I'll start with focusing on the work we've been doing for Rubin-LSST. This is in the context of kind contribution called Popstar LSST, for which basically we produce synthetic stellar catalogs for the LSST stellar content with the TRILEGAL population synthesis code. Right now, we simulate the Milky Way, the Magellanic Clouds. We produce stellar density maps that are actually included in the LSST metric and analysis framework. There are also Jupyter Notebook tutorials available if you want to explore the simulation. And here in the slides, there are a few useful links, and all of this is publicly available and hosted at Noir Lab Astrodata Lab. So what's in this catalog? So basically for each simulated star, we have photometry in LSST, Gaia filters, positional and kinematic properties, stellar properties, like for instance, surface composition and other stellar parameters. And we also include pulsation periods for Cepheids and long period variables. We also have specific quantities, of course, for the binary catalog. Uh, and in total for LSST, we have around 12 billion stars, and the catalogs are complete down to 27.5 magnitude in the R band. Um, okay, these are some examples of the Jupyter Notebook tutorials and what you can do with the simulation. So, for instance, color magnitude diagrams, color coded according to stellar parameters, or galactic components. You can do distribution of expected number counts of specific types of stars, and this is a link of for this kind of Jupyter notebooks. So how do we do this kind of large-scale simulations? Basically, we divided the sky areas using a ILPIX scheme with a variable resolution that depends on surface mass density and also on extinction variation. So you can see here that the resolution increases, for instance, in the bulge, of course, where the density can vary, and also we have larger extinction variation in the bulge of the galactic plane. Um, so this is just a scheme of TRILEGAL, which is again the evolutionary population synthesis code we use to do this kind of simulation. I won't go in details, just want to mention that TRILEGAL starts from evolutionary tracks. We produce isochrones and um, then we need information, of course, on the star formation rate, age metallicity relation, geometry, extinction of the object we want to simulate, including, of course, our own Milky Way, which is currently modeled with these four components, thin disk, thick disk, bulge, and halo. And we also model the extinction, and we can simulate any, let's say, external object given the star formation histories, extinction, so like stellar clusters, Magellanic Clouds, or nearby galaxies. These kind of catalogs can be, let's say, colored in over 50 photometric systems, or in for any filter that for which you have the characterization, and in particular the transmission curves. So TRILEGAL is based on, typically uses parser colibri stellar evolutionary models that covers all the evolutionary phases from the priming sequence to the thermally pulsing AGB stars. And we also have additional tracks for post-AGB and white dwarfs. And it covers a large range of initial masses and metallicities. Um, TRILEGAL also includes a binary evolution module, so we can also produce sim catalogs with interacting binaries. And this is important if you want to model, for instance, a color magnitude diagram like the ones shown here from Gaia Galax. So these are optical UV color magnitude diagrams, and these show how we can better reproduce this kind of observation when we include interacting binaries in the models. As I probably already mentioned, we include stellar variability in TRILEGAL. So for the moment, periods and dominant mode for LPVs and classical Cepheids are available in the LSST simulation, and we have ongoing work to provide updated variability information for Cepheids, and also to add photometric amplitudes and light curves, and eventually also additional variable stars like RR Lyre. This is just a brief slide to show what are other plans to update our TRILEGAL simulation for LSST. We are currently computing the third data release, and a few updates I want to mention are related to the kinematic model that we have recently updated to follow the work of Bond and collaborator based on SDSS data. We also have updated star formation history for the galactic disk and for the LMC. And in this release, we will also add simulated globular clusters. Um, these are some applications and some work that have used this kind of simulation, and I will focus on mainly the aspect of stellar crowding, and also relevant in the time domain science is, for instance, this work of Marcella Di Crescenzo for the light curves recovery with Rubin-LSST and the importance of crowding. So with our stellar density maps produced with TRILEGAL, we can also give estimates of the expected stellar crowding. This is based on an analytic formalism proposed by Olsen and collaborator, And we can do this for each LSST filters as a function of seeing. This is an example of this kind of analysis. So the question is basically, given a scene value, what is the magnitude at which photometric uncertainty due to crowding is dominant? And we have an empirical threshold for this sigma crowd, so the error due to crowding, for which the completeness drops sharply. Basically, you can uh, you can estimate the magnitude limit for which the completeness is well below 50%. Um, this can be done again with using this analytic model and our TRILEGAL luminosity functions that we calculated. And this is an example for the result we are getting towards the bulge region. And these fields are color coded according to the expected magnitude limit due to the crowding for a seeing value of zero point 0.4 arc seconds. We can do the same kind of analysis of incompleteness due to stellar crowding for globular clusters. This is an example of for 47 TAC. This is our color magnitude simulated color magnitude diagram that include the 47 TAC, the SMC, and the Milky Way. And on the right, you see the expected crowding limit as a function of the radius of the cluster. And again, this is for a specific value of seeing, in this case, one arc second, and a threshold for the crowding error of 0.1. And you see that the crowding will severely affect, of course, the very central part of the cluster. So the impact of crowding is also relevant, for instance, for light curve recovery of Euler-Lyre, and this has been shown by this work by Marcella Di Crescenzo. These are simulated light curves in LSST filters. And basically, these plots just tell you that if you take into account the effect of crowding, in this case, for instance, using the TRILEGAL LSST simulation for a particular star, there were 5 nearby stars that would contaminate the observation. And the crowding affects both the mean magnitude that you recover and the amplitude. So the message here is that taking into account the effect of crowding is really important. So that said, unfortunately, LSST data releases won't include information on crowding errors and incompleteness. This is because, of course, the classical method to estimate this kind of quantities with artificial star tests is too computationally intensive for the entire LSST footprint. But of course, this will cause many of the science goals related to science in the galactic plane, bulge, or globular clusters will be severely affected by the lack of this information. And here I'm just showing some of the crowding maps we produce for a specific region and specific value of seeing in the R band. For the bulge, Magellanic Clouds, and Magellanic Clouds. So what we did was to try and come up with a new project to try and solve, let's say, or help to provide the community with measurement of incompleteness and photometric errors due to stellar crowding for each LSST data release. The project just started in October, and it's called SPICE for LSST. And we have, of course, many collaborators that will help us in this endeavor. So the idea is to produce targeted artificial star tests using, of course, the information we already have from the TRILEGAL simulation, So also doing it by simulating realistic stellar population in selected sky regions that will um, probe the relevant ranges of brightness, colors, and densities. And cool. Something cool. Sorry. The next step then is to basically calculate this error amplitudes function of the error amplitudes that are function of brightness distribution and seeing um, for this selected sky region. And then with the help of TRILEGAL simulation, in particular the simulated luminosity function, we will build interpolation routines for any sky region. And of course, this error function will be verified using, for instance, the complete HST fields, and and basically let's say that the accuracy and reliability level that we will require is that it's the one that will meet specific science applications. Um, so to summarize this, basically the deliverables of this project are to provide quick and accurate estimates of the incompleteness, crowding errors with confidence interval for all LSST footprints. And this will be available to the community via the Rubin science platform. But of course, these methods and the software can be adapted for other surveys. And I guess in the context of WST, this can also be relevant for the planning of the observing strategy. For instance, if you have information on crowding, maybe this can help with the fiber placement for the multi-object spectrograph, and in particular, maybe this kind of analysis can also help with the IFS for to put like let's say priors for crowded field blending software like Pamplemuse, for instance. As I mentioned, some science application that can benefit from this kind of work will be mapping the Milky Way in crowded regions, or deriving the star formation history in Milky Way fields and also nearby galaxies, of course, and the characterization of variable starlight curves, and also characterizing faint stellar objects. Um, Now I just want to mention a few aspects that are included in our updates to the simulation. As I mentioned, we computed an updated star formation history of the Milky Way disk based on Gaia data, and we computed the star formation history as a function of height from the plane. So basically, we have the disk structure as a function of age, and this is just showing the solar cylinder that we use to select the data. These are our partial models used for the CMD fitting, and the in the edge metallicity plane. And you see that they cover the relevant expected measured metallicity available from spectroscopic data. The point I want to make about this is that, of course, when you derive star formation histories via CMD fitting technique, there are several caveats. And in this case, we also plan to do a recalibration of the fitted parameters with a better characterization of the population of binaries, because, for instance, for binaries, the orbital parameters, the distribution of orbital parameters is uncertain, and these, of course, can affect the binary fraction that you recover from your CND fitting. We plan to explore a larger range in galactocentric radius, and also to include spectroscopic information to better constrain the star formation histories. And of course, WST observation in this context will be extremely helpful. Um, um, they will be very helpful, as I said, for stellar multiplicity. For instance, this is probably you have already seen this plot a lot of times, but it is just to show how with WST we can really probe larger Milky Way areas with respect to other surveys like Gaia and Formos, which are fundamental, of course, but with WST we will really have a lot of useful information and also about the chemical abundances and kinematics information that can help to put better constraint to our models. Very briefly, this is about the star formation histories of the Magellanic Clouds. In this case, we derive it with deep infrared photometry from the VISTA survey. And again, the method is more the same. We use CMD fitting with TRILEGAL models to derive star formation rate, age metallicity relation, extinction, and distance for both the large and small Magellanic Cloud. And these kind of works are also important for uh, putting constraint to specific stellar evolutionary phases. Indeed, we based our calibration of AGB models on this first work of the star formation history of the Magellanic Clouds, because what we did is to derive the star formation history of this part of the color magnitude diagrams, excluding the AGB stars, because the models are very, very uncertain. So in a series of work, what we did was to use the star formation history as input to simulate with TRILEGAL AGB populations in the Magellanic Clouds, basically varying parameters related to mass loss and third red up in TP-AGB models. We did this with the Colibri code, and we computed a large set of models to find the best fitting models in terms of the reproduction, let's say, of the observed and simulated luminosity function for the entire AGB population of AGB stars in the SMC and the LMC, but also for the population of oxygen-rich, carbon-rich, and the so-called extreme AGB stars. This plot on the right just show that this kind of work are also important for the study of distant unresolved galaxies, because the PAGB stars are expected to significantly contribute to the integrated light. So if you have reliable models, of course, you can also better interpret the observation of unresolved distant galaxies. Um, this calibration was done, as I said, in the Magellanic Clouds, but of course we want to provide a robust calibration in the relevant age metallicity plane. So we are exploring other objects that we can do for this. We can use for this kind of calibration. For instance, the metal-rich regime with M33 and M31, and in particular also the metal-poor regime with local group dwarf galaxies. This is in the context of an HST Leavitt survey, which imaged 19 local group dwarf galaxies from the UV to the optical to the infrared. And this is important because with this kind of observation, we can really well characterize also core helium burning stars, in particular the red helium burning stars and the blue helium burning star sequences. And these this data can be used to constrain, for instance, a core and envelope overshooting in this kind of models, which are uncertain. And regarding AGB stars, using specific medium band filters from HST, we can also have a reliable separation using only photometry. And we are doing this kind of data model comparison for this kind of galaxies. Of course, this works relies on photometry-based identification and characterization of evolutionary stages and chemical types, and also on the star formation rate and age metallicity relation that derive from CMD fitting. But both these kind of aspects can be really improved with spectroscopic data. And I think that in this context, WST again will be very useful also to put constraint on this kind of model, for instance. And in particular, we could also do crowded field IF, IFS, and also we can do also multi-object spectrograph observation for resolved star up to 2 megaparsec. This, of course, will increase the sample of galaxies that we can use for this kind of calibration. But this also means that with spectroscopic information we can put better constraint on the age metallicity relation, and also we can validate and improve the photometric identification of AGB stars, in particular M-type and carbon stars, and of course also red and blue helium burning stars. And with this, I can leave you with the summary, and happy to take any questions.
This was a really, like, let's say, like, excellent talk. Thank you so much. Like, I'm
Thank
really sorry that we couldn't announce this as a synergy talk, because I feel like this has big applications for the galactic working group. And if we could have like some folks from there, because already like we requested to prepare the catalogs for that working group as well. And then like this could be something that could have been of interest to many people, I'm sure. But the good thing is that we're recording this and we're gonna like, distribute this on the YouTube channel so people can watch it. And if they have any comments, like they can come
Of
back
course.
to you.
Sure.
So yeah, any comments or questions from the crowd?
I have
People online?
some questions for
Yes.
Giada. Only clarification, I don't remember the last model atmospheres used in the last update of the TRILEGAL are the Phoenix model atmospheres, or there were other updates about model
Uh,
atmospheres?
so no, we are still using those. Yes, there are no updates regarding
No, okay.
that.
So you are still using the Phoenix ones.
Yeah, then of course for different kind of stellar type to use different types of models. Now I don't have the plot here. I think no, probably not. With all the the spectra that we are using for different kind of stars, but of course for AGB stars we are using COMARC's spectra, specifically calculated for the temperature and the stellar parameters for AGB stars, taking into account also that they can be also carbon stars, so this has to be taken into account, and there are in general specific type of spectra for different kind of stars. There's if you are interested, this is let's see if I have I don't have the plot, but in the paper of Young and
Okay,
Penn,
okay.
yeah, you can see there's a figure when you can
No, I want
immediately
only to know if there were some updates,
okay.
because it's exactly the same paper that I use for the model that I usually calculate.
Okay.
And another question, can you come back to the slide with the zoom on the bulge?
Yes. Oops, this
Can you say
one.
something, can you tell something about more about this plot? I don't understand how do you find this plot?
Okay. So basically, here what you see are the simulated fields with TRILEGAL in the bulge direction, let's say. And these are color coded according to the expected crowding, the expected magnitude limit due to stellar crowding. So when you see like here in the very central
Okay, okay.
region of the bulge, you have that for this specific value of seeing, for instance, we expect that the magnitude limit will be around 18 magnitude. So this means that this basically is your confusion limit. And if
Mm,
you can basically go resolve stars if you go fainter. So
okay. And last question. In one of your last slides, you showed model taking account rotations, right?
yes,
Uh,
let
yeah, this
me
one, this one.
yes.
And why do you choose this value for rotation? There is a specific.
No, these are just this is just an illustrative plot to show what is the effect of specific angular rotation rate on evolutionary tracks when you look it in the HR diagram.
Mm. Okay, okay. Thank
So,
you, Giada. Thank
okay,
you for the talk. Thank you.
thank you.
Any other questions? No? Okay, then I have a question. So on the slide about binaries, I saw something very, I don't know, like nice about the HR diagrams, like the Gaia HR type, like diagrams. And I was wondering if taking into account more of binaries is adding to your sample. Like, is that like the
You mean,
result of the, because I mean, there were like parts that were not there if you're not taking into account the binarity.
but you mean these plots
No,
or the
no.
first, the very first
I
plot?
think like previous slides.
Ah, the okay, yeah.
This one.
Yes.
Yes.
Okay.
So you see like some models like with binaries are introducing other parts to the HR diagram. Is that like the result here?
Yeah, so for instance, here these are like the hot subdwarfs that are
Mhm.
expected to be formed only from the binary channel. So if you, of course, if you do simulation without taking into account um, the interacting binaries, you won't have these this kind of stars, for instance.
Hmm. And what is the assumption here for binarity?
Um, so. I don't remember. This was from. I don't remember exactly the assumption. I will have to check in the paper, and I can let you know. But you mean the assumption regarding like
Like
binary
what was the
tracks
criteria?
or?
Because for example, like with Gaia astrometry, we say that if like for example, like one of the indexes like the um like let's say like if the roof for example is like higher than 1.4, then it means that the five solution astrometry does not work, so you must have like another companion in the system.
Okay.
Like this is like one of the things that we say, but I mean it's not like I mean something
Okay,
conclusive.
okay. So
But
this is based on again this the implementation of the binary evolution in TRILEGAL is based on this the classical BSE code, which is from Arle and collaborator. And what we did in this case was to replace the analytic formulation they have for the description of single stellar evolution with the actual parsec tracks. So this is an improvement, let's say, with respect to this kind of work. But then you have, of course, to assume, for instance, the distribution of orbital parameters for binaries that you are simulating. And in this case, I think this is assumed to be from Mo and Di Stefano papers, if I remember correctly.
okay,
But again,
nice.
there are several uncertainties in that. So yeah, I guess that having more information for also on the distribution of orbital parameters that are expected for different phases would be very helpful, and WST maybe can help with that.
All right. And one general question. So you're already using Phoenix spectra, which is like kind of like the perfect spectra that we can expect in some cases. So what do you think a large homogeneous data set from WST will be adding to your models, eventually speaking, like besides classification? Do you think like it would also help you with calibration, or will you need, for example, like an high resolution window in order to help you for this type of like classification, etc.? Because you have the precision data from LSST. So how can WST give you some specific data?
So I guess that ideally you would want like the perfect complete empirical library so that you can like use a real spectrum for each simulated star given the simulated stellar parameters. So,
But
this,
that's like very computationally
yeah,
expensive. So I
exactly.
was
So, no, no,
thinking,
I
yeah,
mean,
like how many
that's
are you gonna use? And then like star to star is like
okay.
very different. So yeah, like how do you see the role of actual real observation like come into play?
Okay, in terms of improving model atmospheres, I guess that mm, we can probably start to compare the current model atmosphere results and the spectra with what WST will give us. Um, in relevant to be reasonable, let's say in relevant ranges, representative ranges of stellar parameters that can be um, something that can be done and can be helpful for this kind of works, I think.
I especially think like I was like crystal gazing, but then like I was thinking because we're mainly having no idea at the moment about the spectra of very faint stars, like let's say brown dwarfs in like crowded regions, especially like we have like I don't know few maybe spectra in the near infrared of these objects, but then like there's like nothing else. So I was thinking like with Rubin like going to like R band like for the limiting magnitude of 25, then like WST can be like a kick slide on that end.
Mm.
So you have the spectra for the very first time and you can see like what is actually happening in that regime. So I would say like maybe like one of the things that would be like the holy grail here is to characterize like brown dwarfs that are like, I mean, like a spectral type of like L and T could
Okay.
be the thing that is like we're seeing for the very first time
Mm.
and we have like no idea how they look. Because photometrically speaking, I think that is like kind of easy, but if you go through a spectra, it's very difficult because we are not expecting that many lines, right? Also,
Yes.
activity-wise, I think we don't know anything because they have like aurora flares and then like everything else, but we haven't like caught anything so far.
Yeah, I mean, modeling spectra of brown dwarfs is, of course, very complicated. I mean, there are groups that are doing this, that are producing synthetic spectra for brown dwarfs, like the group of the Baraf, Isabel Baraf.
Right.
So the uh, Tucson group, I think, or I don't know if maybe I don't remember exactly the names of the people, but they are doing a lot of work on these, and there are very complicated process for that are going on in the atmosphere of this kind of objects, of course. So any any real information, I think that could be really helpful.
Yeah, no, right. I mean, especially because WST will do like time domain astronomy of these objects. So like that's really something to look forward to because I mean
Yeah.
LSST will give us a lot of data too in that regime, like let's say like
Yeah.
for flares at least. Because I mean if they're flaring or like having like huge, like meaningful stellar activity in the white light, like we can see that too, but also like in near infrared, I think that's very important.
Yeah.
So yeah, questions, comments while Jada is here? Okay, if not, then we are thanking you again. Thank you so much for your time. We really enjoyed this, truly, and have a wonderful day, everyone. Take care. See you around.
Thank you.
Thank
Bye.
you. Bye bye,
Ciao.
Thank you.
everybody.
Bye bye. Thank
Bye.
you.